Welcome to our lecture on difference in differences. We're going to start off with an example, and we'll return to this example later in the lecture using the data from the original study. This is taken from a paper by Meyer et al. From 1995. If you visit the course website, you can click on this link to download a copy. So here's some background. The paper is about workman's compensation and injury duration. So workman's compensation is cash and medical care benefits for work-related injuries in the U.S. This program is run by U.S. states, and the coverage, amount, and type of benefits varies considerably across states. We're going to be talking in particular about something called temporary total disability, or TTD. So TTD means that you're unable to work at the moment, but a full recovery is expected. And for TTD, there's no fixed duration of benefits. So here is the research question from the paper of Meyer et al. Do more generous TTD benefits increase the duration of claims? To study this question, they looked at a policy experiment in the state of Kentucky, and KY is the abbreviation for Kentucky. So policy experiment means it wasn't a real experiment, it was a change in a policy that could maybe serve as an as-if experiment, or kind of like a quasi-experiment. So in particular, on July 15th, 1980, the state of Kentucky increased the maximum TTD benefit from $131 a week to $217 a week. Here is a graph on the right of the slide that shows the implications of this policy change. So there are two groups of workers that we're going to be thinking about here. They are illustrated in the diagram. You can see at the bottom we have the low earnings group. These are the folks whose previous earnings were between E1 and E2. Then we have the high earnings group. These are the folks whose earnings were above E3. So their previous earnings were high. Now, the graph at right illustrates the change in the policy. So you can see the solid line shows what the policy was before the increase, and then the dashed line shows how the policy changed after the increase. So let's start off before the increase. So the vertical axis shows the weekly benefit amount, or WBA, and we have three values on there from bottom to top. We have WBA min, we have WBA max before, and we have WBA max after. So if you take a look at the schedule of benefits, what's going on here is there's a minimum benefit. That's WBA min, and that's completely unchanged by the policy. What the policy has done is it's changed the maximum benefit, which used to be WBA max B, up to WBA max A. So if your earnings are sufficiently low, then you're just going to receive the minimum benefit. That's the same before or after the policy. But once your earnings hit E1, then the benefit that you receive is going to be equal to your earnings up to a particular point, and that point is when you hit the benefit max. So that benefit max used to be at E2, and now it's moved all the way up to E3. So what this means is that there's two relevant groups. There's a group of folks who were between the minimum and the old maximum. So those are going to be called the low earnings group. Those are people who are going to get benefits according to that benefit schedule. So they're unaffected by the max and they're unaffected by the min. Their benefits are determined by their own earnings, their own previous earnings. Then we've got the folks who are between E2 and E3. We're not actually going to be looking at them. Now we're going to be looking at the folks E3 or above. So those were people who previously would have received the maximum benefit WBA max before, and after the policy change, their earnings, their benefits are going to jump up to this higher maximum. So the policy only affects these high earners. It does not affect the low earners. And their weekly benefits are increasing from the old max to the new max, while these low earners are totally unaffected. So the nature of the data set we have here is actually repeated random samples. So we have a random sample of workers before and after the policy change. So this is not a panel data set, it's a repeated cross-section. In our data set, we know the date of the injury, we know their earnings before the injury, and we know how long they stayed on the benefits, so we know the duration of benefits. All right, so that's the example we're going to talk about, and before we can return to it, we need to discuss the identification strategy that we're going to use to learn the effect of this change in benefits on the duration of benefit receipt. So compared to our earlier lectures on causal inference, the new ingredient this time is a time dimension. So previously we used the notation y0 and y1 to denote the potential outcomes when untreated or treated at a single unspecified moment in time. Our new notation is as follows: y subscript t of 0 and y subscript t of 1 denote the potential outcomes at a specified moment in time t. So I'm now using subscripts for time, and I'm using parentheses to show which treatment state we are considering. So you can remember this by thinking about P in parentheses is the same letter as P in potential outcomes. So that means that yt of d is your potential outcome at time t if we intervene to set your treatment equal to little d. The new idea that we're going to use in this lecture is making use of the time dimension to produce a before and after treatment comparison. So the time dimension gives us a new way to think about bringing in information that could be relevant for understanding a causal comparison. We're going to start with a very simple two-period model. At the end of the lecture, I'll say a little bit about more complex models with more time periods. In this two-period model, we'll assume that we have an observed outcome, y subscript t, and we observe this outcome in two time periods. T is before and t is after. I'm actually going to write the words out in full because I think it's a lot less confusing than using time indices that are numbers, because we're also going to be using 0 and 1 to denote untreated and treated. So I'll just write out before and after. Between these two periods, some people are treated, D is 1, and the rest are not. So the before period is a point in time before anyone has been treated, and the after period is a point in time after some people have been treated, because the key idea here is going to be that not everyone gets the treatment. So in this two-period model, each person has a pair of potential outcome time series. So here are the time series. If you are treated between the time periods, then your potential outcome time series is going to be y before of 1 and y after of 1. If you are not treated between the time periods, then your potential outcome time series is going to be y before of 0 and y after of 0. These potential outcomes are linked to the observed outcomes as follows. Y before is the observed outcome in the before period. That's equal to 1 minus d times y before of 0 plus d times y before of 1. And the observed outcome y after is equal to 1 minus d times y after of 0 plus d times y after of 1. Whereas before we had a single equation that linked a single observed outcome to two potential outcomes, here we have two equations. Each of those equations links an observed outcome to two potential outcomes, but we've got one equation for each of two time periods. That's because we have a two time period model. The causal effect that we're going to be after in this lecture is a second period effect. So it's a causal effect in the after period. We're going to call this delta for short, and delta is defined as y after of 1 minus y after of 0. So this is a comparison of potential outcomes, treated minus untreated, in the after period. In other words, the period after which some folks were treated. All right, now you may be wondering, what exactly is this y before of 1? It's not the potential outcome if you're treated in the first period. It's not. Remember, the treatment date is actually in between the before and after period. So y before of 1 is in fact the potential outcome in the before period if you are treated after this period. And you might say that's a bit weird. Nobody has been treated in the before period, right? So why are we writing y before of 1? I mean, that person hasn't received the treatment yet. It kind of seems like we're making a distinction that isn't really necessary. So, in other words, why in this before period, where everyone isn't treated, why are we distinguishing between y before of 0 and y before of 1? Or how could a potential outcome possibly depend on a future treatment? It does look weird, but it's actually not so weird if you stop to think about it. And what we're trying to do is we're trying to create notation that is sufficiently flexible to accommodate what is sometimes known as an Ashenfelter dip, and more generally as anticipation. So this idea comes from a paper from Ashenfelter in 1978. Roughly speaking, anticipation means that if I know I will be treated tomorrow, I may change my behavior in ways that affect my outcomes today. And here's a quote from the paper, quote, all of the trainee, which is to say treatment, groups suffered unpredicted earnings declines in the year prior to training. So this was a paper that studied the effects of our government training program, and the folks who were in the training program had lower earnings, unpredictably lower, in the year prior to training. So it may be that people anticipating that they were going to be trained changed their behavior beforehand. And there are many situations where that might be plausible. When that happens, that's called anticipation. And what you'll notice is that we have a potential outcome notation that can accommodate it. So in particular, we're allowing y before of 0 and y before of 1 to be different. Here's a graphical illustration of two things. First of all, this anticipation idea, or an Ashenfelter dip, and second of all, an illustration of what our causal effective interest really is. So I'm going to explain this picture in some detail because later in the lecture we will look at two very similar pictures using the same color scheme and using the same notation. So the horizontal axis here is time, and the time axis runs from before to after. These two periods, of course, refer to the period before treatment and after treatment. So in between them, I have put the date of treatment. On the vertical axis, we have outcomes. So we have y subscript t of d. So we're going to plot in every time period these different potential outcomes. Let's take a look at the before period. In the before period, we can see that there are two values on the plot, one of them in red and one of them in blue. I'm going to use red to refer to untreated potential outcomes throughout this lecture, and I'm going to use blue to refer to treated potential outcomes. So in the before period, we've got two potential outcomes, y before of 0 and y before of 1. The way I drew things here, they're not equal to each other. So the way I drew things here is exactly like the Ashenfelter dip, because I'm in a situation where the potential outcome of the folks who will eventually be treated is lower in the before period than if they had not actually been about to be treated. So in this example, I've drawn things so that if you're going to get the treatment in this treatment date period, then your potential outcome before that date is lower than it would have been if you weren't going to get the treatment. That's an example of an anticipation effect. So if there were no anticipation, it would mean that the red and blue dot would be in the same location in the before period. Now let's take a look at the after period. So in the after period, I have added an additional annotation to the plot. So I've added a little curly brace and a delta. So remember that the treatment effect that we're interested in here is a second period treatment effect. That is to say, delta is equal to y after of 1 minus y after of 0. So the causal effect that we want to learn about is the difference between those two potential outcomes in the after period. It's very natural to want to study the causal effect after treatment because, well, if you think about the way that causality runs through time, we're interested in how the things that we intervene on are going to cause effects in the future. So we want to learn the causal effect on the future, presumably, not the causal effect on the past, which is to say anticipation. So it's sort of natural to study this delta. But we're also going to focus on a particular subgroup of people. We're going to focus on the treated. So you probably recall, as we discussed in our lecture on local average treatment effects, that there are different effects besides the average treatment effect. One of them is the treatment on the treated effect. We're going to be focusing on this here for a couple of reasons. One is it turns out that's what difference in differences can tell us. But also, this is really the group of people for whom we can make a before and after treatment comparison. So the folks who are never treated, we can't really compare them to themselves over time in a treated versus untreated state. So it's actually quite natural that what we're ending up with here is a TOT effect. I will write this as TOT for short, but it is important to remember that this is the TOT effect in the second period. So again, the causal effect of interest here will be a second period effect. We're going to be talking about the average difference between the treated and untreated potential outcome in the after period, but we're going to be restricting our attention to that effect averaged over all the folks who actually do get treated. So it's a treatment on the treated effect, and I will write TOT for short, but again, just remember, this is the effect in the second period. To introduce the difference in difference design, I first want to show you a related but simpler design. I'm going to call this the before and after design. So what is this? Well, this is a comparison of observed outcomes for treated people. We're going to look at after minus before. So this is a within-person comparison. After minus before, and since these people are treated, we're comparing you in your treated state to you in your untreated state, but of course, they're in different time periods. So one of the most important things to remember, of course, is the fundamental problem of causal inference. I can never observe the same person at the same period of time in both the treated and untreated states. So what we're doing here is we're saying, well, maybe you in the past, which is to say you before you were treated, is a good comparison to you in the present after you were treated. It doesn't necessarily solve the problem of causal inference because, of course, there could be many reasons why something changes over time that are not merely the fact that you were treated. But we're going to talk about what assumptions would be needed for this particular approach to give us a valid causal comparison. Okay, so this is a stepping stone to the difference in difference design. In this average TTD claim duration example, we could look at the high-income folks, so those are the only ones who are actually affected by the policy change, before and after the cutoff date. So remember, that was a repeated cross-section. So we could look at high-income folks in the second cross-section, take the average of the duration, and compare that to the average for the folks in the before period. All right, there are two assumptions. And one of these is something we're going to relax later when we move up to the diff-in-diff approach. The first assumption is no anticipation. So we are saying that on average, the y1 in the before period and the y0 in the before period are the same. At least that they are the same for the folks who actually do get treated. So this is like saying on average, the red and blue dots in the before period on the previous slide, a couple of slides back actually, are in the same location for people who are eventually going to get treated. Okay, so the second assumption here is no trend. This says that y after of 0 and y after and y before of 0 are on average equal for the people who will eventually get treated. So let's put this into the language of the TTD example. So this first assumption, no anticipation, would say for high-income people, on average, y before of 1 is the same as y before of 0. So there's no anticipation effect for the high income people on average. No trend would say that for high income people, y after 0 is the same as y before of 0. So again, this is only for the people who are eventually going to be treated. So we're only making an assumption here for the high income people because they're the folks for whom D is 1. They're actually exposed to the policy. And here's the theorem. It turns out that under these two assumptions, the TOT, which is defined as y after of 1 minus y after of 0 for the treated, is equal to the difference of means y after for the treated minus y before. So it's a very, very simple causal estimand. There is a proof here on the slides, but rather than going through the derivation in math, I would prefer to go through the derivation on the graph. If you would like to read through this with some more explanations, you can take a look at the course notes on causal inference, which you can access at treatment-effects.com. You can check out the chapter on Diff-in-diff, and you will see a long description of this relatively simple argument. But I think it's much clearer to see it visually. So here again is a graph of time on the horizontal axis and outcomes on the vertical axis. It's set up exactly the same as the one I showed you before, but the precise lines that I've drawn differ. So as before, red is the color that I will use for untreated potential outcomes, and blue is the color that I will use for treated potential outcomes. Also, I have indicated the treatment effect of interest using this curly brace and a delta. So that is in the after period, we're comparing y1 to y0. All right, so now let's see how these assumptions can be read off of the graph. And I just want to be clear before I show you this that in the derivation, we talked about how the potential outcomes merely need to be equal on average, and they merely need to be equal on average for the treated, whereas in the graph, I'm drawing it in a slightly stronger way to just show that the potential outcomes are exactly equal. So this situation I'm showing you in the graph only needs to hold on average. All right, so let's take a look here. No anticipation. Well, what does that mean? That means that in the before period, the y1 is equal to the y0. And what is no trend? Well, no trend means that the y before of 0 and the y after of 0 are the same. So that means that the red line is flat. So no anticipation means that the blue and red dots are the same in the before period. And no trend means that the red line is flat. Well, what does that give us? It's a triangle, and it's a right triangle. If you join those red and blue lines, and then you connect to the dots right where my causal effect delta is located on the right-hand side of the plot with the curly brace, you've got a lovely little right triangle. So the causal effect is the short leg of the triangle. What, in fact, can we measure? Well, for the treated, we don't get to observe any parts of that red line. We can't observe y before of 0 or y after of 0 for the treated, because the treated are precisely the people who are on the blue line. We never get to see their red line because since they were treated, their observed outcomes are those on the blue. Okay, so even though we can't observe the red line, what can we observe? Well, we can observe y before of 1. Now, if we assume that that's equal to y before of 0, all right, then if we assume that y before of 0 is equal to y after of 0, what can we do? Then we can conclude that the difference of y after of 1 and y before of 1 must be equal to delta. So again, just take a look at that triangle. If it's a right triangle, so if the y before of 1 and the y before of 0 are equal to each other, and if that y before 0, y after of 0 is a flat line, we get this right triangle. So you can just read off that the difference of the two blue vertical coordinates just has to be equal to delta. So it's almost so obvious it's difficult to think about how you would prove it, but if you go back to the previous slide, you can see a full proof. All right, now, so the obvious problem with this, of course, is that we've made some assumptions that may or may not be plausible. So the next thing that we're going to do is we're going to try to relax perhaps the least plausible of those assumptions. So what's wrong with before and after? Well, this assumption of no trend may be quite implausible. What it basically says is that nothing else is changing. So here we are, some people got a treatment, and before the treatment we measured them, after the treatment we measured them, and we're just assuming that any way that they changed over time must have been due to the treatment. But we all know that there's lots of things that could change over time. The economy could go into a recession, people could gain new skills, there could be changes in the economy that privilege one industry over another, there could be a global pandemic. There are so many different sorts of things that could change over time, so that the idea that there's no trend, the idea that nothing else changes, in other words, the idea that if you were not treated, then your potential outcome would have been the same in the before and the after period, it just starts to sound quite implausible. So, what difference in differences does instead is, rather than assuming there's no trend, it tries to estimate that trend by using another group of people. So we're going to take a look at the untreated people who are in the control group, and we're going to use them to try to estimate this counterfactual trend over time in untreated potential outcomes. That's really all there is to it. So whereas the before and after design was a purely within-person comparison for folks who get the treatment, Diff-in-diff is going to combine between-person and within-person comparisons. That's why there are two differences. We'll have a new assumption called parallel trends, and this assumption will replace the no trend assumption that we used before, but we'll retain no anticipation exactly as above. So here is the parallel trends assumption. It says that for people who are in fact treated, the average difference in their before and after potential outcomes when untreated are equal to the average difference in before and after potential outcomes when untreated for people who did not, in fact, get the treatment. That's a mouthful to say out loud, so let me try to make it a little bit more specific by referring to our TTD example. So D equals 1 are the high earners, and D equals 0 are the low earners. What this says is, on average, the trend in untreated potential outcomes, before and after, is the same for high earners as for low earners. So if we imagine, suppose there's some kind of macroeconomic change, like a recession, and Y is some outcome that could be affected by that macroeconomic shock. So what this is sort of saying is that on average, that shock and the way that it occurs over time is affecting these two groups the same. It's affecting them the same insofar as that shock matters for their untreated potential outcome. So it's saying, look, the high earners, they got treated. But if they hadn't, then they would have experienced their Y0 potential outcomes before and after. What we're saying here is that we can use the low earners to study what that trend would have been for the high earners. So it is a claim that the trend is comparable for the two groups of people. We're not saying that Y after of 0 is the same for these two groups. We're not saying that Y before of 0 is the same for these two groups. We're saying that the trend, which is to say the difference, is the same for these two groups. So this is just a bit more on the parallel trends assumption. So again, the trend in untreated potential outcomes is the same on average for the treated and untreated. This allows time invariant unobservables to drive selection into treatment. So it could be that there is some unobserved fixed effect that makes some people more likely to be treated than others. If so, then we're taking differences. It's actually be differenced away. What it does is it rules out selection based on time-varying unobservables, so transitory shocks. So some folks can select into treatment based on time-invariant unobservables, and we can also handle kind of like macroeconomic shocks or trends that are hitting everybody the same. So we can handle a time trend of that kind. So what we're ruling out is selection based on time-varying unobservables, so like kind of individual specific trends. This is fundamentally an untestable assumption, and the reason is that we never observe Y after 0 for the treated. So this is an assumption, and you can't get away from the fact that it's an assumption. I should actually mention we never observe Y before 0 for the treated either, but our no anticipation assumption is what is telling us that we don't have to worry about that potential outcome. So this is a fundamentally untestable assumption, but if we think it's plausible, then we obtain the following result. No anticipation plus parallel trends tells us that the TOT effect is a difference of two differences. So you look at the after minus before comparison of outcomes for the treated. You look at the after minus before comparison of average outcomes for the untreated, and you take the difference of the two. That turns out to be equal to the TOT effect. Now, once again, I do have a proof on the slides, but I think it's probably better for you to read through the proof in the lecture notes than to hear me say it out loud for a couple of reasons. One of those reasons is that actually all the intuition is contained in the picture. So I'm going to show you a picture in a moment. I'm going to explain the intuition. And at that point, I think you might find it, if you like, quite easy to come back and look at these slides, or to look at the write-up, which you can find, again, at the course, I should say, at my treatment effects course website in the lecture notes there, treatment-effects.com. So I will skip this derivation, and I will take you to the picture. We've got a triangle, just like before when we looked at the before and after design, but this one is no longer a right triangle. Okay, so what's going on here? Well, the thing that I've changed is there is now a trend in the untreated potential outcomes. It is no longer the case that y before of 0 was equal to y after of 0. So you can see that means that the red line goes up over time, and the amount by which it goes up, I have written that in red at right. That's delta naught. Okay, so what do we do here? Well, if we just did the before and after comparison for the treated, what would we get? I've written that at left in blue. I've called that delta 1. That's what we looked at in the before and after design. We said just take y after minus y before. Well, that gives us delta 1. But is delta 1 equal to our treatment effect of interest? Well, no. It would be if that red line were flat, but the red line is not flat. So the difference between y after of 1 and y before of 1, in this diagram at least, is bigger than the actual treatment effect of delta, which is a comparison of the treated versus untreated potential outcome in the after period. So what do? Well, we can see from this diagram that the blue delta 1 is actually equal to the sum of the red delta naught and the black delta. So delta is what we want, and all we need to do here is if we can learn delta 1, then we need to subtract delta 0 to obtain delta. That is precisely what difference in differences does. It takes the before and after difference of the treated, that's delta 1. It then takes the before and after difference of the untreated, that's delta naught, and it subtracts them. So under the assumption of parallel trends, this is going to give us the causal effect of interest. So to implement this, you can very simply compute the sample means after treated minus before treated, after untreated minus before untreated, and take the difference of the two. This is equivalent to running a regression of y, your outcome of interest, on D. D is an indicator for whether you are eventually treated or not. So notice that D has no time subscript. D is just D subscript I to indicate that you're someone who's in the treatment group. So in our TTD example, D would be 1 if you are a high earner, so that you're going to be subject to the policy change. We also include in the regression a dummy variable which I'll call post of T. This is a dummy variable that equals 1 in the period after and 0 in the period before. And finally, we include an interaction. So by now we've seen many examples when we can run a relatively simple regression with dummy variables and interactions to learn causal effects of interest under different kinds of identifying assumptions. This is yet one more example, and one that uses a time dimension to do so. So if you run this regression, then the coefficient on the interaction, delta, is exactly your TOT. And again, that is a difference of differences. And you can work through the logic of why that's the case by plugging in all the possible values of these dummy variables and interactions, and then making your way through the logic based on the meanings of these coefficients. The regression approach makes it a bit easier because we can then compute standard errors. If necessary, we may want to add some control regressors. I'll talk a little bit about that later. So while you can compute the difference in difference estimator just by comparing the means, people usually do this by running a regression instead. So a panel is a random sample of individuals whom we observe in multiple time periods. A repeated cross-section is multiple random samples taken at different points in time that presumably do not include the same people. Or rather, if they do, it's purely by random chance that one of the same people or more of the same people happened to be in both samples. So the way I've been speaking about things, I mentioned a within-person comparison and a between-person comparison. It sure made it sound like you need panel data for difference in differences. And indeed, causal effects are within-person effects. But the whole name of the game when we do causal inference is to use between-person information to identify them. And the reason why that works, we can just think about a simple randomized controlled trial, is because expectation is a linear operator. And I don't know why I wrote the word expectation twice on this slide, but that just really drives home the point that expectation is a linear operator. So for the same reason, actually difference in differences works just fine if we have repeated cross-sections. So it doesn't actually matter if we observe the same people in the before and the after period. This linearity of expectation means that everything is going to go through just as if we had seen the same people in both periods. And this will also work with the regression approach just as well as it does with the simple comparison of means approach on the slide. So that's very convenient, of course, because the empirical example that we've been looking at in this lecture does involve repeated cross-sections. Let's take a look. Here we're going to load some of our favorite packages: Broom, Estimator, Tidyverse, Model Summary, and the Wooldridge package contains the data set from this paper. So the first thing that I'm going to do is I'm going to filter the data to extract only the observations for Kentucky, because the paper actually includes data set from Michigan as well, but here we just want to look at the data set for Kentucky. So what I'm going to do here is I'm going to rename some variables. So the variable high earn in the original data set is what I'm going to call treated. So that is the treatment indicator. If you're a high earner, you get treated, otherwise you don't. The variable af change, which stands for after change, is the time dummy. So I'm going to call that post. So it equals 1 after the treatment occurred, so in the post period. And the outcome variable is duration. In the data set, it was called durat. I don't really like that, so I'm just going to call it duration. I feel as though we can afford those extra letters ION. So now I'm going to run 3 different regressions. And I am using heteroscedasticity robust standard errors using the lm-robust command. If that is not familiar to you, you can check out my lecture on robust standard errors a couple of lectures ago. And I'm going to run 3 different regressions. So the first one that I'm going to run is what I'm calling the naive regression. So this is a regression where I'm going to subset my observations to only come from the post period. So I'm only going to look at the time period after the treatment has occurred for some subset of people. And I'm going to run a regression of the log duration on treated. So I'm looking at the difference of means of log duration for the high earners and the low earners in the second period. I'm calling this naive because everything that we know about causal inference suggests that this shouldn't work. A naive comparison of means in the second period probably should not identify the causal effect of interest, because these 2 different groups of workers are very different from one another indeed. One group is high earners and one group is low earners. They're probably in different professions. The kinds of on-the-job injuries that they get might be very different, and that might be the real cause of any difference that we observe in the duration of their benefit claims. So that's my naive estimator. We don't expect it's going to work very well. I will then estimate a BA model. BA stands for before and after. I am now, in that particular model, we only look at the people who are treated. So I'm taking the subset of folks who have treated equal to 1. And now we're regressing log duration on post. So what does that do? Well, that takes a difference of means after minus before for the treated, which is exactly what the before and after approach does. So is that going to give us the right answer? Well, it requires the assumption of no anticipation, but also the assumption of no trend. So if both of those assumptions are satisfied, then this BA effect will work. Finally, I have DD, which is my difference in differences approach. Here, I will be regressing log duration on the interaction, I should say on treated, post, and the interaction. That's what that little asterisk does in R. It expands to include both the levels and the interaction of those two variables. So in this case, I will get the right answer if I look at the coefficient on the interaction, provided that there is no anticipation and that there are parallel trends. So whereas BA requires that there are no trends, DD only requires the trends are parallel. And I'm going to put all the results together into a nice little list so that we can display them and see whether the differences matter. And here they are. I have my naive model, I have my before and after model, and I have my difference in differences model. And let's take a look. So with the naive model, it is the coefficient on treated that would give us the causal effect of interest, assuming the model assumptions were correct. Okay, so we're estimating a causal effect of 0.45. Remember, this is on the log scale, so that's actually a pretty sizable effect. So this says that the folks who were treated, the folks who got the more generous benefits, were staying on these benefits 45% longer, and there's quite a small standard error there. That's a very, very sizable effect. Let's take a look now at the before and after approach. In this approach, we're only looking at the people who were treated, but we're comparing them before and after. So you can see that the sample sizes are not the same in the first and the second column. So the first column is only using one time period, but all of the individuals. And the second column is only using the treated individuals, but 2 time periods. So the sample sizes are not the same as a consequence. So they're approximately the same, but they're not exactly the same. So in the BA column, we can take a look at the coefficient on post. Again, we get a positive coefficient, but it's much smaller. So it's 0.2. So this would be a 20% increase in the duration of the claims from this more generous benefit. And again, there's a pretty small standard error there relative to the size of the coefficient. All right, so the naive estimator, we really have no reason to expect that that's correct. And we see the before and after has actually cut the effect size by more than 50%. So what about the difference in difference estimator? Well, what's kind of nice about this table is that we build up to the difference in differences by first looking at the coefficient on treated, then looking at the coefficient on post, and finally looking at the interaction. So in the difference in difference regression, we're including treated, post, and the interaction, and it is that interaction term that we're interested in, treated times post. So here we're getting an estimate of 0.19, which is actually quite close to that from the before and after. So what that seems to suggest here is that the assumption of no trend maybe wasn't so bad after all, or, put it another way, when we made the assumption of parallel trends, the trend that we estimated for the untreated group, which we then brought over to kind of fill in the missing potential outcomes for the treated, was pretty close to flat. So we're getting a very similar coefficient estimate. Now, the standard error actually has gone up by almost 50%. That is pretty common. In fact, it may be almost universal. The reason is that it's harder to estimate an interaction than it is to estimate a main effect. It takes a larger sample to precisely estimate an interaction than a main effect. There's actually a great post from some years back on Andrew Gelman's blog about this. But you can also see that the number of observations in the difference in difference regression is larger. And that is because this regression uses both time periods and both groups of individuals. All right, so that brings the main part of this lecture to a close, but I would be remiss if I did not mention at least some of the recent papers in the difference in difference literature that have caused a huge stir, and some of the main issues that have emerged in recent empirical practice as important, difficult, and in need of good solutions. So let me first of all raise this parallel trends assumption, which is a really crucial one. In fact, it is the crucial assumption that we use in difference in differences. Well, following the original paper by Meyer et al., we worked with the log of duration. So that means that we require an assumption of parallel trends in logs. But it turns out that if parallel trends holds in logs, it likely fails in levels and vice versa. So there's something a little bit strange about the way that this parallel trends assumption works. Namely, being parallel geometrically is a property that is not invariant to different sorts of transformations. So there's something that's a little bit uncomfortable about this, because in some sense, if you're going to deploy a parallel trends assumption, you sort of need to know what the right scale of the variables is, what are the right units to have measured them in. The same is not true, actually, for simple comparisons of differences of means. For example, if there's no treatment effect in a randomized controlled trial when I measure the outcome in levels, there will also be no treatment effect in logs. But the parallel trends assumption is quite different. And for this reason, there is a need for you to actually specify the units in a meaningful way. So if you want to understand some more about why this might be unattractive and why it might actually suggest that difference in differences isn't such a valuable identification approach as it may have seemed at first glance, you could check out some of these recent papers. In particular, this Roth and Santa Ana paper is quite interesting, and there's a slightly older paper as well from 2020. So I'm not saying that this means you can't do diff-in-diff, but it does mean that there's something a little funny about how assumptions that you make could be quite sensitive to the precise way that you specify the units of the data in ways that we wouldn't normally worry about in other models because they don't matter. All right, what about anticipation? So I just talked a little bit about this parallel trends assumption and how it can be a bit strange. Well, what would happen if we assumed parallel trends but did not assume the no anticipation effect? Well, we could actually still get a meaningful causal effect. So I'm going to define what I will call the anticipation effect for the treated. So this is the period 1 effect for the people who eventually get the treatment. So it's comparing their before outcome when treated to their before outcome when untreated. And a slight modification of the usual difference in differences argument shows that you can write the difference in difference effect as the TOT minus the AET. So if you want to get rid of no anticipation but assume parallel trends, then difference in differences no longer gives you the TOT, but it gives you the difference between the TOT, which is the period 2 effect for the treated, and this AET effect, which I should point out, that's my own coinage. I made that term up. I don't know what other folks call it, but that is the period 1 causal effect for the treated. So is this interesting? Well, I mean, potentially, it means that if your difference in difference effect is positive, and if you think that the anticipation effect could only be positive, well, then you've still learned something about the TOT. If you'd like to learn a little bit more about the difference between anticipation and endogeneity, there is a nice paper here that I have linked on the slides. You can click on them and view that paper. If you'd like to see my derivation of this decomposition for the difference in difference into the TOT and the AET, you can take a look at my treatment effects lecture notes. What about inference? Well, inference in difference in differences is genuinely difficult, and I chose an empirical example that avoids almost all of those complications. So if you recall, we had repeated cross-sections, so we had 2 random samples, one before and one after the policy change. Random samples are IID in each of these cross-sections, so there's absolutely no need for clustering. I did use robust standard errors, but there was no need to think at all about how to do clustered inference or anything like that. Now, in true panel settings, it would be typical to cluster over I, whether these are individuals or US states. But here's the tricky thing. So inference based on the central limit theorem actually requires many clusters. And this is not always going to be the case in some difference in difference examples. So this is a very active area of research, thinking about the right way to do inference in difference in differences and in other cluster settings. There's a tremendous literature. There's lots of interesting papers. But if you want to see a very quick overview with some pointers to some of the more interesting papers, I'd recommend that you check out this review article of Roth et al., and in particular, section 5 of the review. Another issue that arises is staggered treatment timing. So above, we focused on a two-period model where treatment occurred between the two periods. But more generally, we could have more than two time periods, and we could have treatment occur in any period from 1 up to capital T. Typically, in many policy examples, once a unit is treated, it remains so. So you might think about staggered rollout of a policy or a program where different locations get that policy sooner or later, but once the policy is in place, it sticks around. All right, well, in this case, we need potential outcomes for every possible treatment start date, including never, because we might have a particular group of folks or a particular unit that is never treated. So, for example, we might need to have a potential outcome Y subscript 2016 of 2014. Well, that would be a U.S. state's potential outcome in 2016 if it experienced a Medicaid expansion beginning in 2014. So this gets quite complicated. If you are willing to roll with the notion that treatment effects are homogeneous, then you could extend the regression approach from above to include basically to run a two-way fixed effects model. And there are many papers that do this. However, if treatment effects are heterogeneous, this approach can fail extremely badly, and it can give results that are basically uninterpretable. This is a little bit complex to explain, but there's a good summary of the recent literature, again, in this review article of Roth et al., in particular in section 3. Finally, you may wonder about this parallel trends assumption. Can we relax it? Can we evaluate it? And in practice, you'll see a lot of folks who use more than two periods. Typically, if you have additional pre-treatment periods, they will compare the pre-trends, in other words, the trend in outcomes before the treatment date, between the groups who are eventually treated and the groups who are not. So this is sometimes called comparing pre-trends. Another thing that you will sometimes see is placebo tests, where you run difference in differences with a fake treatment date, one that doesn't actually correspond to the real date. You know, these kinds of exercises can be suggestive. There are certain sets of auxiliary assumptions under which they might tell you something useful. But strictly speaking, you know, neither of these actually provides any direct evidence for or against the parallel trends assumption. So they're very common in practice, but they're really not addressing the fundamental issue, which is that these assumptions are not testable. You might also wonder if we could relax the parallel trends assumption. And the answer is perhaps. So perhaps parallel trends doesn't hold unconditionally, but it does hold conditionally on covariates. If so, then we could perhaps combine difference in differences with some selection on observables approaches. And we've already learned about some of those: regression adjustment and propensity score weighting. So unsurprisingly, if you want to use them, you're going to require an overlap assumption. So again, a great resource if you're just beginning to dip your toe in the waters of the voluminous recent difference in differences literature is this Roth et al. Review article. And if you visit my website, download the slides, you can click on this link to be directed to the article. Section 4.2 in particular talks quite a bit about the various ways of relaxing parallel trends, and also some prospects for doing so using these selection on observables approaches.